Module 1, Lecture B, Syntax and Variables. By the end of this lecture, you will be able to create variables that represent electrical quantities with clear names and appropriate numeric values. Write arithmetic expressions for voltage, current, resistance, charge, energy, and power calculations. Use comments and formatting to make engineering code easier to read and verify. Core Python syntax, variable naming. Clear variable names make Python engineering programs easier to understand and maintain. Names should reflect the physical meaning of the values, such as voltage or current, so the connection to the real system is obvious. This reduces confusion, helps others verify calculations, and makes future updates safer. Good variable names help separate similar electrical quantities, such as input, output, measured, and rated voltages. A clear name should show whether a value is a design limit, a real measurement, or a nominal rating. This makes programs for equipment like battery packs and motor drivers easier to understand and less prone to mistakes. In Python, names must follow the language's syntax by using single identifiers without spaces or reserved punctuation. Good professional practice goes further by using a consistent naming style, which makes programs easier to read and navigate. Clear, disciplined names help distinguish patterns, such as measured versus calculated values or component-level versus system-level values, and they act as useful documentation during testing, debugging, and communication. Python code, variable naming. Use clear variable names to make engineering calculations easier to understand. In Python, variable names cannot include spaces, so choose readable names and include units when they help clarify the meaning. We store the main circuit values using clear names: a 12-volt supply, a 24-ohm load resistance, and a battery charge of 1800 coulombs. These descriptive quantities make the circuit calculations easier to understand and maintain. Use Ohm's law to find the load current by dividing the supply voltage by the load resistance. The result gives the current in amperes and shows how much current the load draws for the given voltage and resistance. Power delivered to the load is found by multiplying the supply voltage by the load current, giving a result in watts. A measurement time of 60 seconds is then set for calculating energy use over that interval. Energy used over 1 minute is found by multiplying the load's power in watts by the time in seconds. This gives the energy in joules. The program prints a concise summary of key electrical results: supply voltage in volts, load resistance in ohms, load current in amps, load power in watts, and energy used over 60 seconds in joules. This gives a clear overview of the main calculated values and their units. The script summarizes a simple circuit by using the supply voltage and load resistance to find the current with Ohm's law. It then calculates the power delivered to the load and the energy used over 60 seconds. Finally, it prints these key values, giving a concise overview of the circuit's performance. Naming variables. When writing Python programs with physical quantities, use clear, descriptive names that show what each value represents. In electrical engineering, names like supply voltage or load resistance give immediate context, while vague names like value or number can be confusing. Clear naming helps distinguish concepts such as current, voltage, and resistance, reducing mental effort and supporting correct calculations. In Python, Engineering variables should be named clearly and briefly by combining the measured quantity with its system context. For example, names should indicate whether a voltage belongs to a battery or resistor, or whether a current is an input, output, or leakage value. Precise naming makes programs easier to review, discuss, collaborate on, and debug. Clear names in Python make engineering calculations safer by showing what each number represents. Because Python does not know whether a value is in volts, ohms, or joules, names should make units, assumptions, and whether values are measured or calculated obvious. This discipline helps prevent unit mix-ups and turns raw numbers into a clearer description of the system. Python code. Naming variables. Use clear variable names to make engineering code easier to read. Names should describe the electrical quantity they represent, and including units helps prevent common mistakes. The code stores the supply voltage as 12 volts and the load resistance as 6 ohms. Using descriptive names that include both the quantity and unit makes the values easier to understand and helps prevent mistakes in later calculations. Use Ohm's law to find the load current by dividing the supply voltage by the load resistance. Then find the load power by multiplying the supply voltage by that current. This links the calculations directly to the circuit's voltage, resistance, current, and power. The battery charge is set to 3600 coulombs, representing the available electric charge. To find how long the battery can operate, divide this charge by the load current in amps. The result is the operating time in seconds before the battery is depleted. The code makes operating time easier to understand by converting seconds into hours, using a more familiar unit. It also creates a short summary, reminding readers that clear descriptive names help show what values represent, what roles they play, and what units they use. The code prints a clear summary of 3 electrical values: supply voltage in volts, load resistance in ohms, and load current in amperes. Including each unit with its value makes the output easy to understand for engineering use. The code displays key electrical results: load power, found from the supply voltage and load current, and operating time, based on battery charge and current draw. It ends by highlighting that clear, descriptive variable names make engineering calculations easier to understand. The script uses clear variable names to calculate basic electrical values. It defines the supply voltage and load resistance, then uses Ohm's law to find current, calculates power from voltage and current, and estimates battery operating time in hours. It then prints a concise summary of these results, showing how descriptive naming improves readability and helps reduce mistakes. Electrical quantity variables. In Python for electrical engineering, use clear named values for physical quantities, such as voltage and current. The names should show what the quantity represents, and when needed, its condition or location, such as a battery voltage. Descriptive names make calculations with similar quantities easier to understand, test, and less prone to mistakes. Choosing appropriate numeric values is as important as clear naming because it helps a program match the real-world engineering context. Electrical quantities may require whole numbers or decimals, depending on the measurement and needed precision. Always make the scale and units clear, such as distinguishing amperes from milliamperes to reduce errors before calculations begin. In engineering Python workflows, clear names for electrical quantities connect code to real lab and simulation data. Naming values precisely, such as distinguishing different kinds of voltage or power, helps others understand the data and avoid costly confusion. This makes programs more accurate, readable, and useful for collaboration in electrical systems. Python code, electrical quantity variables. Use clear variable names for electrical quantities and include unit suffixes to reduce engineering errors. Simple arithmetic checks can also confirm that each variable represents the intended meaning. Define a clearly named variable for the source voltage and set it to 12 volts. Using a descriptive name that includes the unit makes the code easier to understand and helps prevent calculation errors later. Set the load resistance to 240 ohms so it can be used in later current and power calculations. Including the unit in the variable name makes the value clear and helps prevent engineering mistakes. Use Ohm's law to find the load current by dividing the source voltage by the load resistance. The result, measured in amperes, shows how much electric charge flows through the circuit. The time interval for measuring charge is set to 60 seconds. This provides a fixed duration for later calculations involving electrical charge transfer. Transferred charge in coulombs is found by multiplying the load current in amperes by the measurement time in seconds. This uses the basic relationship that charge equals current over time, showing how much electrical charge moves through the circuit during that period. Load power in watts is found by multiplying the source voltage by the load current. This uses the basic electrical power relationship and shows how much power the load consumes in the circuit. Energy use in joules is found by multiplying the load power in watts by the measurement time in seconds. This gives the total energy consumed over that time period. The code creates a results list to organize key electrical values for display. Each item groups a label, a value, and a unit, covering voltage in volts, resistance in ohms, and current in amperes. This makes the calculated quantities easy to present clearly and compactly. The results list is extended with entries for charge, power, and energy. Each entry stores a label, its calculated value, and the correct unit: coulombs, watts, or joules. This keeps the key electrical quantities organized for easy display and interpretation. The code first prints a header introducing the results as electrical quantity variables. This gives context for the values that follow and helps make the output clear and organized. The code goes through each result, taking the quantity name, value, and unit, then prints them in a clear formatted line. Each value is rounded to 3 decimal places, making the calculated electrical quantities easy to read and compare at a glance. The script uses a 12-volt source and a 240-ohm load to calculate basic electrical quantities. It applies Ohm's law to find the current, then determines the charge transferred in 60 seconds, the power consumed, and the total energy used. Finally, it prints these values with their units, rounded to 3 decimal places, giving a quick summary of the circuit's behavior. Engineering expressions. Ohm's law. Ohm's law explains how voltage, current, and resistance are connected in simple circuits. Voltage drives charge flow, current measures that flow, and resistance limits it. With resistance unchanged, more voltage means more current. With voltage unchanged, more resistance means less current. This relationship helps calculate missing electrical values and check that components, power supplies, and wiring will work safely together. When using Ohm's law, choose the form that matches what you need to find and interpret it physically. Voltage is the push needed to drive current through resistance. Current is the flow caused by voltage across resistance. and resistance is how much a component opposes that flow. These relationships turn circuit behavior into measurable values for checking designs and choosing components. When using Ohm's law, first make sure voltage, current, and resistance are in consistent units, such as converting milliamperes or kiloohms when needed. The law works best for components with steady resistance, like fixed resistors, and may be less reliable for devices such as diodes or motors. Even with these limits, Ohm's law is a key tool for understanding and checking circuit behavior. Python code, Ohm's law. Practice Ohm's law by using clear variables to represent circuit quantities, writing arithmetic expressions to calculate them, and printing compact results for quick checking. Using Ohm's law, the current in the circuit is found by dividing the voltage by the resistance. With a voltage of 12.0 volts and a resistance of 470 ohms, this gives the current flowing through the circuit in amps. Use the current and resistance to calculate the voltage, then compare it with the known value to check consistency. Next, multiply the current by 30 seconds to find the total charge that flows. Finally, multiply the voltage by that charge to determine the circuit's energy use in joules. Use Ohm's law to find electrical power by multiplying voltage in volts by current in amps, giving power in watts. Then convert current to milliamps by multiplying by 1,000, and convert resistance to kiloohms by dividing by 1,000. These conversions make circuit values easier to read and work with. The output presents key circuit values in readable engineering units. Voltage is shown in volts to 2 decimal places. Resistance is converted to kiloohms with 3 decimal places, and current is shown in milliamps to 2 decimal places. These formats make the values clearer and easier to interpret in practical circuit analysis. The output reports 3 key circuit values, each rounded to 3 decimal places: the charge transferred over 30 seconds in coulombs, the energy used in joules, and the power dissipated in watts. Together, these values give a quick summary of the circuit's electrical behavior. This script gives a quick demonstration of Ohm's law using 12 volts and 470 ohms. It calculates current, checks the voltage from current and resistance, then finds charge over 30 seconds, energy used, and power. The printed results show these values in practical units, helping confirm how voltage, resistance, current, charge, energy, and power are related. Resistance calculations. Resistance controls how easily charge flows through a circuit and helps explain circuit behavior beyond voltage and current alone. Wires, sensors, and other components all resist current, which can affect performance and safety. In calculations, the numbers should match physical intuition. Higher resistance means less current for a given voltage, while lower resistance allows more current to flow. In circuits with multiple components, total resistance depends on how the parts are arranged. Components in series increase resistance because each one adds another obstacle to current flow, while components in parallel lower resistance by giving current multiple paths. Correctly identifying the circuit layout is important to avoid problems such as overheating or inaccurate measurements. Resistance calculations are important in professional design and troubleshooting. Engineers use them to choose components such as LED resistors, and technicians use them to diagnose appliance problems. In areas like electric vehicles and renewable energy, resistance affects efficiency and reliability, so calculations must be clear, accurate, and matched to the circuit's needs. Python code, resistance calculations. Engineering expressions link circuit concepts to calculations. Resistance values help determine how current behaves, and clear variables make the results easier to check. The script stores two key circuit measurements, an applied voltage of 12 volts and a current of 0.025 amperes. These values describe the potential difference and charge flow, and they are needed to calculate resistance using Ohm's law. Use Ohm's law to find the resistor's resistance by dividing the voltage in volts by the current in amps. The result is the resistance in ohms, shown to 1 decimal place for a single resistor in the circuit. Store the resistance values for 3 series resistors, 220 ohms, 330 ohms, and 470 ohms. These values will be used to calculate the circuit's total resistance. To find the total resistance of 3 resistors in series, add their resistance values together. The combined resistance is then displayed in ohms, rounded to 1 decimal place for a clear result. Store the 2 parallel resistor values, 1000 ohms for the first resistor and 2000 ohms for the second. These values will be used later to find the circuit's total resistance. To find the total resistance of 2 resistors in parallel, add the reciprocals of their resistances and then take the reciprocal of that sum. The result gives the combined resistance in ohms, typically displayed to 1 decimal place. Set the supply voltage to 9 volts across the series resistor network. Then find the circuit current by dividing this voltage by the previously calculated total series resistance, giving the current in amperes through the entire series circuit. Convert current from amps to milliamps by multiplying the amp value by 1000. Then display the result to 2 decimal places so the series circuit current is clear, precise, and easy to read. The code compares the total resistance of a series circuit with that of a parallel circuit. It checks whether the series resistance is larger, stores the true or false result, and then prints a message showing the outcome. This script applies Ohm's law and basic resistance rules to simple circuits. It finds that 12 volts and 25 milliamps correspond to 480 ohms, then compares a series network totaling 1020 ohms with a parallel pair totaling about 666.7 ohms. With a 9-volt supply, the series circuit draws about 8.82 milliamps. Overall, the example shows that series connections increase total resistance, while parallel connections reduce it and allow more current to flow. Power calculations. Power calculations show how quickly electrical energy is converted into forms like light or heat. By combining voltage and current, engineers can determine whether components, power supplies, and batteries can safely handle a circuit's demands. Electrical power can be calculated in different ways depending on which quantities are known. Voltage and current give power directly, while current with resistance highlights heating and losses, and voltage with resistance lets you find power without first finding current. These forms help engineers choose the most efficient calculation while keeping the circuit behavior clear. Power calculations depend on correct units, proper order of operations, and understanding what the result means physically. Since power in watts describes how quickly energy is converted, it helps estimate heat, system capacity, and how long an energy source can support a load. The same reasoning applies across different scales, from chargers to electric motors. Clear arithmetic makes results easier to check and helps prevent engineering problems such as undersized parts or shorter battery life. Python code, power calculations. power calculations show how voltage and current are related. Using clear variables makes formulas easier to check. And watts measure how much energy is converted each second. The circuit is defined using three known values: a voltage of 12 volts, a current of 0.75 amps, and a resistance of 16 ohms. These describe the electrical potential, charge flow, and opposition to current, and they provide the basis for calculating the circuit's power and energy. Power is found by multiplying voltage in volts by current in amps, giving a result in watts. This tells how quickly energy is being used or produced in a circuit. This calculation finds power from current and resistance. It squares the current in amps, then multiplies by the resistance in ohms, giving the power in watts. To find power from voltage and resistance, square the voltage in volts and divide by the resistance in ohms. The result is the power in watts. Set the operating time to 3 hours, then estimate energy use by multiplying the device's power based on its voltage and current by that time. The result is the total energy consumed over the 3-hour period, measured in watt-hours. This section introduces 3 common ways to calculate electrical power. It shows power from voltage and current as power equals voltage times current, then power from current and resistance as power equals current squared times resistance. It also shows power from voltage and resistance as power equals voltage squared divided by resistance, with each result reported in watts. The code displays the circuit's energy use over a chosen time period. It uses the calculated energy in watt-hours and the duration in hours to show the total energy consumed. The code verifies that 3 ways of calculating electrical power give the same result, using voltage and current, current and resistance, and voltage and resistance. If all 3 match, it records the comparison as true and prints the result. This provides a quick check that the equivalent power formulas agree. This script calculates electrical power in watts using 3 equivalent formulas: voltage times current, current squared times resistance, and voltage squared divided by resistance. It also estimates energy use over 3 hours in watt-hours. The program prints the results and checks that all 3 power calculations match, confirming the formulas are consistent. Readable engineering code. Meaningful comments. In engineering code, useful comments explain why calculations are being done, not just what the code does. They help connect the program to tasks like modeling, design checks, data processing, and result verification. Clear comments make code easier for others to review and easier to understand when it is revisited later. Good code comments should explain what the code does not make obvious, rather than repeating the code line by line. Use them to record assumptions, units, sources, limitations, and design choices, such as whether an engineering value is based on worst-case conditions or an idealized estimate. This makes comments useful embedded documentation that supports checking calculations, catching errors, and maintaining accuracy. Effective engineering comments should be clear, precise, and kept current. They should explain the reasoning behind the code without interrupting its flow, using familiar terms and specific details when needed, such as the exact device limit being checked. Outdated or vague comments can mislead engineers, while accurate comments support testing, troubleshooting, and understanding design decisions. Python code. Meaningful comments. Good engineering code is easier to verify when it is readable and well documented. Comments should explain the intent behind the design, while values should make units and assumptions clear. The circuit's nominal values are set from the design notes: a 12-volt supply, a 24 ohm load resistance, and a sensor current of 0.08 amps. These values define the basic operating conditions and provide the starting point for later electrical calculations. Use Ohm's law to estimate the load current by dividing the supply voltage by the load resistance. The result gives the current in amperes flowing through the load under the given conditions. Add the load current and sensor current to find the total current in the circuit. Then compare that total with the regulator's limit of 0.75 amps to make sure the circuit stays within the regulator's safe operating capacity. Load power is found by multiplying the supply voltage by the load current, giving the power the load consumes for thermal assessment. A safe limit of 8 watts is then used as the maximum allowable power to help ensure the system does not overheat. Calculate the remaining safety margins for both current and power. The current margin is the regulator limit minus the total current, showing how much capacity is left before the regulator reaches its maximum. The power margin is the safe power limit minus the load power, showing how much additional power can be handled without exceeding thermal limits. Clear labels make these results easier to interpret and check. This example prints key current values in a readable engineering format. It shows the load current, the total current including the sensor, and the remaining current margin against the regulator limit, each rounded to 3 decimal places in amps. Together, these outputs help confirm that the circuit is operating within safe current limits. The code reports the load power found from the supply voltage and load current and shows it in watts to 2 decimal places. It also reports the remaining power margin by comparing the load power with the safe limit, making the available headroom clear. A final message highlights that comments should document engineering intent, assumptions, and constraints. This script checks whether a circuit design stays within safe electrical limits. It uses the supply voltage, load resistance, and sensor current to estimate the load current, total current, and remaining current margin against a 0.75 amp regulator limit. It also calculates load power and compares it with an 8-watt safety limit. The printed results summarize current, power, and margins, so the design can be verified for safe operation. Inline comments. Inline comments in engineering code should explain why a calculation matters, not simply repeat what the code does. Good comments connect computed values to the physical system, such as identifying a supply voltage or safety margin. This makes the code easier to understand, review, and verify later by others or by the original author. Effective inline comments should be short, precise, and focused on information the code does not already make clear. In electrical engineering, comments are especially useful for identifying units, data sources, conversions, and whether values are ideal, measured, or design limits. Clear comments make assumptions visible, which helps others verify and understand the calculations. Use inline comments sparingly so code stays readable and uncluttered. The most useful comments explain non-obvious decisions, assumptions, constraints, or reasoning behind calculations. In engineering work, they can mark test points, calibration factors, conservative estimates, or temporary troubleshooting values. Good comments support the process by making the code clearer and more trustworthy. Python code. Inline comments. Use comments and notes to make code easier to understand without cluttering it. Inline comments should explain the engineering intent, clear units should support calculation checks, and concise notes should keep the code readable. The test uses a 12-volt supply from the bench power source, a 220 ohm resistor, and an operating time of 30 seconds to estimate the circuit's energy consumption. Use Ohm's law to find the circuit current by dividing the supply voltage by the resistance. Then, convert the result from amperes to milliamperes by multiplying by 1000, which makes the value easier to compare with common electronic component ratings. Calculate the resistor's power by multiplying the supply voltage by the current, giving the rate of energy converted to heat in watts. Then find the total energy used by multiplying that power by the test time in seconds, giving the result in joules. Set the resistor's power limit to 0.25 watts based on its datasheet rating. Then compare the calculated power dissipation with this limit to determine whether the design is safe. If the dissipation is less than or equal to the limit, it is within the resistor's acceptable range. The example prints P circuit results in a readable format, current in milliamperes, power dissipation in watts, and energy used during the test in joules. It also reports whether the resistor's power dissipation stays within its rated limit, helping confirm whether the design is safe. This script checks a simple circuit with a 12-volt supply and a 220-ohm resistor. It uses Ohm's law to find the current, then calculates the resistor's power and the energy used over 30 seconds. It also verifies whether the power stays within a quarter-watt rating, helping confirm the circuit is operating safely. Code comments. Comments in engineering code explain the purpose and context behind calculations, not just what the program does. They make it clear whether values represent things like measured voltage, rated current, or estimated resistance. Good comments help classmates, instructors, technicians, and even the original author understand the reasoning later. Good code comments should explain intent, assumptions, and context, rather than repeat what the code already shows. Note where values come from, what units they use, and why assumptions are valid, such as measurement conditions or whether a value stays constant. In calculations, clarify whether results are instantaneous or averaged. This helps the program accurately represent the real-world system it models. Comments make code easier to verify by explaining the program's logic and the purpose of each section. In engineering, they are especially important for noting assumptions, unit conversions, and how data should be interpreted. Comments should be concise, accurate, and kept up to date so they support the calculations rather than mislead future readers. Python code. Code comments. Good comments clarify the engineering intent behind a design and provide context for future readers. Clear notes also make later verification easier, while documenting units and assumptions helps prevent confusion. The circuit values are set as 12 volts for voltage, 0.5 amperes for current, and 24 ohms for resistance. Including explicit units keeps the quantities clear and helps prevent confusion in calculations. For a current flowing for 10 seconds, the total charge is found by multiplying the current by the time. The energy delivered is then found by multiplying the voltage by that charge, giving the total energy transferred during the time period. Calculate measured power by multiplying voltage by current. Then estimate the theoretical power by squaring the voltage and dividing by the resistance. Comparing these two values through their absolute difference shows how closely the measurement matches the expected result and helps identify any discrepancy. The code prints a clear summary of the key engineering inputs used in the calculations. It labels the output, then shows the measured voltage, measured current, and assumed resistance with appropriate decimal precision. Together, these messages make it easy to quickly verify the main values before using them in further analysis. The output summarizes three calculated electrical quantities with clear units. It shows charge from current and time in coulombs, energy from voltage and charge in joules, and power from voltage and current in watts. Each value is rounded to 2 decimal places for a clean, readable result. The code compares 2 ways of calculating power to confirm they agree. It prints the difference to 4 decimal places, making any mismatch easy to spot. This checks whether power from voltage times current matches power from voltage squared divided by resistance. This script uses basic electrical relationships to calculate key quantities from voltage, current, resistance, and time. It finds charge from current over time, energy from voltage and charge, and power in 2 ways, from voltage times current and from voltage with resistance using Ohm's law. It then prints the measured values and calculated results, including the difference between the 2 power values, to check that they are consistent. In this lecture, you learned to create variables that represent electrical quantities with clear names and appropriate numeric values. Write arithmetic expressions for voltage, current, resistance, charge, energy, and power calculations. And use comments and formatting to make engineering code easier to read and verify. In the next lecture, Lecture C, we will go over built-in tools. Thank you for your attention. See you all in the next lecture.